Hello, my name is Isan Zhang. Thank you for your interest in our paper. Let me introduce it for you, and let's begin. First, we will give you a short 1-minute preview. In this paper, we focus on source-free unsupervised domain adaptation. To fully utilize source knowledge, we propose to transfer the class relationship. We first regard the classifier weights of the source model as class prototypes to compute class relationship, and then propose a novel probability-based similarity by embedding the source domain class relationship. Finally, we propose to embed the proposed similarity into contrastive learning in a unified form. Here both class-aware and instance discrimination contrastive losses are employed. We combine the proposed method with existing representative methods to evaluate its efficacy in multiple SVUDA settings. That was our preview. From now on, we will provide more details about our work. The first is the introduction section. Currently, many UDA methods have been proposed that jointly learn from the source and target data. But they would be unapplicable for some real-world scenarios involving privacy, such as medical images and surveillance videos, because the source domain data cannot be accessed. Thus, more recent methods focus on source-free unsupervised domain adaptation. Under this setting, the labeled source data are no longer accessible when training the target model, but the pre-trained model in the source domain is provided. Some methods assume that the source hypothesis, such as the classifier or whole model, contains sufficient knowledge for the target domain. For example, SHOT transfers source knowledge by directly aligning features with the fixed source classifier. Another line of work assumes the source model already has some semantic structure and then utilizes the local neighborhood information of the feature space to enforce similarity in the output space. Despite this progress, what knowledge is to be transferred remains an open question. In this paper, we first ask, what knowledge should we transfer to facilitate the learning of unlabeled target domain data? We propose to transfer the class relationship represented by the similarity of classifier weights. Actually, the class relationship is domain invariant since the same class in the source and target domains essentially represents the same semantic in spite of the domain discrepancy. For example, the computers are always more similar to the TV than the scissors. Then we introduce our proposed method. Here we first introduce the basic model used in our paper. We follow SHOT where a new fully connected layer and batch normalization layer are appended in backbone network. The classifier consists of a fully connected layer and a weight normalization layer. When the model is transferred to the target domain, the classifier is fixed. The inherent semantic and visual relationships among different classes are consistent across domains, regardless of distribution discrepancy. Inspired by this, we propose to explicitly transfer class similarities. We first obtain the class similarity matrix from the classifier of the source model. Specifically, the classifier weights are regraded as class prototypes. We normalize classifier weights and use their cosine similarity to construct a class similarity matrix. In this matrix A, the diagonal elements are 1, and the off-diagonal elements range from -1 to 1. A larger value means that two classes are more similar. Our proposed class relationship embedded similarity is based on output probabilities, and contains two terms. The first one is the traditional intraclass term, which is the sum of product of the same class probability. The second term is a new interclass term. It is the sum of the products of all different classes and is further weighted by the class relationship matrix. Using the first term alone cannot represent the true similarity in feature space, since matrix A shows the relative location of prototype in feature space. Introducing the interclass term can accurately express the relationship between two samples. Inspired by the success of contrastive learning in different tasks, we propose to use our new similarity for contrastive loss. The contrastive loss consists of a query sample, a key sample, and many negative samples. It makes the query sample close to the key sample and away from negative samples. Original contrastive loss used cosine similarity of features, Here we replace it with our class relationship embedded similarity. To conduct contrastive loss, we use a teacher-student architecture following MoCo. The query feature is the probability produced by the student model. And the key features and negative features are probabilities from the teacher model. Given the unified contrastive loss format, we instantiate it into two losses according to different positive and negative pairs. The first one is class-aware contrastive loss. The query feature is the probability of the strong augmented view of a target sample, and the key feature is the one-hot probability from pseudo-label class of its weak augmented view. The negative samples are one-hot probabilities of classes except pseudo-label class. This class-aware contrastive loss can be seen as an improved version of fix-match and is only used if the target sample is high-confident. The second loss is instance discrimination contrastive loss. The positive pairs are probabilities from the two strong augmented views of the same target sample. The negative samples are probabilities from other samples in the same training batch. This instance discrimination contrastive loss can learn discriminative feature of target domain data. Next is the experiment section. We conduct experiments on different domain adaptation settings. The first one is single-source unsupervised domain adaptation. Our method achieves SOTA performance on Office Home, Office 31, and VisDA datasets. Our method also surpasses UDA methods on the Office Home and VisDA datasets. We also test our method on multi-source domain adaptation. In our method, we directly combine all source domains into a single domain, and the problem can be converted to single-source domain adaptation. Our method also brings considerable improvements. We also test our method on partial set and open set domain adaptation. Our method can bring consistent improvement on different baselines. We also provide detailed analysis, including component-wise ablation studies in Table 5 and comparisons with different similarities in Table 7. Our class relationship embedded similarity can produce relative high entropy predictions and alleviate overconfident problem. Our method is still effective under transformer backbone and greatly surpasses UDA methods on Office Home datasets. Then this is our last section, the conclusion. We propose a novel class relationship embedded similarity that can more accurately express the sample relationship in the output space. We propose two contrastive losses that exploit our design similarity. We combine our method with existing representative baselines in multiple SVUDA settings and achieve state-of-the-art performance. This is our last slide. Thank you for listening to our presentation.